I hope you can see the slides.
Yes, we can.
Thing. Okay, let us start. So today we'll talk about what is known as Huckel MO theory. And this Huckel MO theory deals with pi electrons. Okay, and it's a better theory than particle in a box kind of approach for especially for conjugated molecule. Okay, so let us take this example. You know this molecule. This is, what is this molecule? Ethene or ethylene. Okay, is it ethene?
Sir, buta 1,4,1,3 diene.
At least you are giving attention. Let us deliver it. So this is butadiene. Okay. Now you know that you have a for this molecule you have this uh, sorry. Just a minute. Let me draw it properly. You have the sigma framework. Okay, and then you have this on each carbon you have one unhybridized d orbit. It's fine because sigma framework is made by this sp2 hybrid orbital. You know, all of you know, I'm sure. So
Yes.
in order to describe this pi and this p orbital will form pi bond, no? They form pi bonds. This. And now we want to have a theory for these pi bonds, these pi molecular orbitals. Okay. So let us start like this. I have 4 carbon atoms. So for the timing, we'll consider only the pi bonds. So let us number them as C1, C2, C3, C4. And on each carbon, you have one p orbital. Sorry for the bad drawing. But this is how it is. Okay. Now, if I have a molecular orbital description for this, what will be the molecular orbital? How would I do? You know the framework, no? The form.
Linear combination.
Yeah. So you will call. Okay, I'll take a linear combination of this C1. Let us call this chi1. This is chi2. This is chi3. This is chi4. And this is going to be C1 chi1 plus C2 chi2 plus C3 chi3 C3 chi4. Isn't it? And then next step would be to calculate this script E. To do a variation calculation, no? You remember script E?
Yes.
This is going to depend on these parameters C1, C2, C3, C4 in this case. So you calculate. So you have to calculate this. And then what should I do? I should do this, no? I should be doing this. This is fine with all of you?
Yes, sir.
We have done this. So once we do this, we will get 4 equations. In this case, no? 4 parameters. So you'll get 4 equations if I do this. Is it fine with all of you?
Yes, sir.
Yeah. Let me write down this. Okay. So let us do what to do. Now, these 4 equations I can write in a matrix form. You remember? So I'll have a matrix like this. What this matrix is going to be? Tell me. You know. Please tell me.
H minus.
Yeah. So remember here you don't have A, B. Your nomenclature is different. It's 1, 2, 3, 4. No. The first term in this case will be H11. You had HA. Remember? We had
Yes,
done it
sir.
for H2 plus minus script T. Isn't it? What is the next term?
H1 to minus
Minus what?
Minus script T into over 1.
15 to
S12. Isn't it? Next one is
1 3.
minus
Script E S13.
the last one.
H14 minus script T into S14.
So you are convinced, no? There will be 4 cross 4 matrix.
Yes, sir.
So what will be the next term? Next, say, row. This is going to be
H21.
H21. What about the next term?
Script E into S21, right?
What about this?
H22 minus script E.
Yeah, this one. Repeat. This one.
H24 minus it script T is.
Because I can do a mistake. No, I'm not writing on blackboard. When you write like this, you can make mistakes. What about this? Oh, this one is
H31 minus script E into S31.
then
H32 minus script T S32. H33 minus script T S34, right?
what about this one?
Script T into S41. H42 minus script T into S42.
This one
H43 minus script T into S43.
and this one.
H44 minus script T.
So this is the matrix, and this matrix, you know that earlier we called this matrix. I didn't call anything, but you have a determinant for this matrix, and that determinant is called secular determinant. I might have not used the term, but that is called secular determinant. Now you have this C1, C2, C3, C4, Okay. Now, before we analyze this matrix, you know that ideally one should do what? One should not have an inverse of this matrix, and you should take the determinant of this matrix to be 0 and solve it. That is what you should do, isn't it? Okay.
Yes, sir.
So now let us see, this is the molecule, no? Sorry, huh? All the orbitals should be of same size because I'm drawing it with hand.
Sir, same size means same coefficient.
Yes, yes, yes. We'll discuss that. Yes. This is a structure, like this is not an MO. This is just a orbitals. Okay. Before combining atomic orbitals. Now the point is, if I now calculate, say, the overlap of this is 1, this is 2, this is 3, this is 4. What about S14? S14 is, you know that it has to be like chi1 times chi4, isn't it? Chi1 star, but chi1 star is
Chi1.
chi1.
It is
Yeah, I'm just
already
writing it here. So this will have some value, obviously, but you see that 1 and 4
Zero.
are quite far away actually. Ideally, it should have some value, but they're quite far away, so I can approximate this to be 0. They're not strictly 0. They're far away. Okay? And not only S14, what about H14? H14 is also this integral. And I am also considering this to be 0. Now these integrals H14, H2, these are called, they have a name. This is called resonance integral. Okay. And if you analyze it very carefully, you will see that in resonance integral, there will be one integral which is called exchange integral. How many of you heard about exchange integral? I think I did not mention. I talked about Coulomb integral, but exchange integral I did not talk about. If you want, you can go and read about it. This exchange integral is there. Anyway, so this is resonance integral. Now this is also an approximate it to be 0 because they are far separated. I'm assuming this to be 0. Not me, it is the Huckel's assumption. What about now if I do so let me write down this matrix again. Huge, this matrix, no? Now this H11 is the energy itself, no? This is energy, no? This is not 0, okay?
Yes, sir.
This is energy. And this also has a name. This is called Coulomb integral actually. This is Coulomb integral. And I assume this to be equal to something like alpha. I'm calling it alpha. And Huckel assumed that all the Coulomb integral, like this one, H22, H33, H44, all are equal and they are equal to alpha. Okay? They're all equal and they are equal to alpha. These are Coulomb integral. And another assumption is all the overlap integrals, not only S14. So it basically means what? Even if I take S12, this is 0. But if you do a real calculation, you'll see that S12 is 0.525 or something like that. It's not 0. Okay? An assumption. Is it okay with you? And this is due to Huckel or Huckel. Okay? Are you following, all of you? And Huckel also assumed, okay, let us see that anything like this, H14 is 0, okay. But if I have a situation like H12, neighbors, nearest neighbors. This H12 is, they are connected, no, they are just next to each other. H23, they are same, equals to H34, and they call them, like Huckel assume this to be a constant, and this constant is called beta, the resonance integrals. Okay, are you convinced, all of you? These are assumptions, so these are very crude assumptions. So this, but only if you have this assumption you can come up with a solution, easy solution. Okay, let us do this now. Are you guys there? Anish?
Yes, sir.
Yeah. So now this guy, this first term is H11 minus epsilon. No? So what is H11?
Alpha.
Yeah. So let us do it. Alpha minus epsilon. Okay. What about this, the second term, H12 minus this one?
This will be beta.
This will be beta, but then all the S's are 0.
0.
0.
Yeah. So what about H13?
0. 0.
0.
Yeah, because this is true for even H13 also. No? So this is 0. What about the fourth term?
That is also 0.
0. Actually, what about this one? H21 minus epsilon S12. What about this
This
term?
will be beta.
Should be beta, no? What about next one? H22 is alpha.
Alpha minus script, right?
50. Third term, 23.
This is beta.
Fourth term,
This is 0.
what about this third one?
0.
H31 is, okay, 0. H32, they are connected, no?
That is beta.
Yeah. What about the third one, H33?
Alpha minus script T.
What about the fourth term?
It
H34
is
is,
also
they are connected,
beta.
no? They are
Beta, right?
connected, yes. Okay, now H41,
That is 0.
H42,
That is also 0.
H43,
This is beta.
and the last term.
Alpha minus script T.
Okay, and you also have this, no? Okay, this is fine. Now this is equal to 0. So I can do one thing. I can divide all the terms by, I just multiply this from left by this 1 by beta. Can I do this? Just multiplying. If I multiply with 1 by beta, what I'm going to get? This 1 by beta will go inside, isn't it? And
then
each
we'll take
term,
one.
each element will get multiplied by 1 by
Yes.
beta or get divided by beta. So I don't have space here. Let us go to the next slide. So the first term is going to be alpha minus script E divided by beta. This is fine. What was the next term? It was beta. It was beta.
Is 1.
Yeah. So next term is going to be 1. And then you had 0 and 0, no?
Yes, sir.
What about this term?
1.
It was beta. So 1. This was, then next one is,
Alpha minus script T by beta.
yeah, all the diagonal terms you know that like this. What about this one?
There is 1.
1, then 0.
0.
0.
What about this? 0.
0.
0.
This is
1.
1. This is,
Alpha minus E by beta.
this
1.
one 1, I think.
1.
Yes, 1.
This one 0. 0. This is 1. Okay, because multiply 0 with 1 by beta, it will be 0 on your right. And let us assume Let us take this x. I can call it x.
Yes, sir.
I can call it x, no? So if I call it x, what I'm going to get, this matrix is becoming now x 1 0 0. This one looks quite nice, no? 1 x 1 0 0 1 x 1 0 0 1 x. This fine?
Yes, sir.
So now what you should do, actually now you should take this matrix, take the determinant of this matrix equal to 0 and get 4 solutions, isn't it?
Sir, how we will solve this matrix, this determinant?
Yeah, you don't know how to expand a determinant? You have to
Sir,
expand this determinant.
3 cross 3, but if, sir, it will be, sir, greater than, then it is so
So
difficult.
you have polynomial in x to the power 4, isn't it? And this will give you 4 roots. And this will give you 4 solutions that correspond to 4 solutions. So Anish, you can expand 4 cross 4 determinant.
Yes.
Yes. Okay, we're not going to do it now. So we'll do some simpler thing now, and then I'll tell you how to do it. Okay. See one thing, that x is always along the diagonal. Can you see that? Whatever the x is always along the diagonal. See? Isn't it? Always along the diagonal. So now let us, this determinant has a name, I told you. This is called secular determinant. And this matrix has a name. This is called Huckel matrix or Huckel matrix. Okay? Fine? Now, simplest, so let us do the simplest possible system. What is the simplest possible system for pi electron?
So ethylene.
Yeah. So this is what it is. So let us do ethene. So you have, I'm just drawing these pi orbitals, sorry, p orbitals. Okay, and this is C1, this is C2. Now this is your task to tell me what is this matrix is going to be. So the orbital is going to be like that, no? MO is like C1 chi1 plus C2 chi2, isn't
It's a
it?
2 by 2 matrix. 2 by 2.
Yeah, it is going to be a 2 by 2 matrix, no? So what is this 2 by 2 matrix? Can anyone tell me? So I have already showed you how to construct for 4 cross 4. Now I'm asking you a question,
At
how
1,
to do it for 2 cross 2.
X1 1 X.
So I
Yeah.
told you that
A diagonal
diagonal elements are always x, no?
X. Yeah.
X. And what
1
about, and you see that next to it is always 1 here, 1 here, 1 here. Huh? So what is going to get? What is going to get? You are going to get 1 here. Because they are nearest neighbor, no? Here. You have only 2 atoms, 2 p orbitals. And then you have this C1, C2, equal to 0. Now, can you solve this determinant?
plus minus 1.
This is going to be x square minus 1 it equal to 0. So x has a solution either plus 1 or minus 1. This is fine. So basically you have 2 allowed energies, isn't it? Because you remember what is x. Let us go to the next slide.
So alpha minus E by beta.
So let us take x is equal to minus 1. Then minus 1 is equal to alpha minus 50 by beta. And that gives you a 50 as, tell me,
Alpha plus beta.
this is, I'm calling it strip E1. This is alpha plus beta. And if I take x equal to plus 1, then this one becomes plus 1 is equal to alpha minus 50 by beta, that means script. Now, which is higher in energy, which is lower in energy?
Alpha minus beta will be higher.
Higher.
Yes, sir.
Any other suggestion? You have two pop. It could be other way, no? But I said
Yes.
this is epsilon 1, this is epsilon 2. That's a hint.
Epsilon 2 is lower, I think.
Why?
Sir,
So
epsilon
actually,
2 will be higher.
you see that alpha and beta, if you calculate, both are negative. This resonance integral and the Coulomb integral, if you calculate, both are negative. So basically means that I have two energy levels. This is alpha plus beta, and this is, okay?
Okay, sir.
So basically bonding MO, this is I call it bonding MO. Of course, we are considering only pi electrons. How many electrons are there in this p orbitals in case of ethene?
Mm.
One on each carbon, no? So how many electrons total? Tell me.
So 2.
Two,
Two
and they are going
electrons.
to go here, isn't it? It's fine. They are going to go to the bonding one. Okay. Now let us compute the MOs. So take x is equal to -1 and put in the equation. They put in the equation. This is -1, -1, 1, 1, C1, C2, 0. And what it will give you, you know how to multiply matrix. This will minus C1 plus C2. This is one equation equal to 0, or C1 minus C2 equal to 0. Although you have two equations, actually we have one equation practically. This is C1 equal to C2. This fine? So if I call, so phi 1 is C1 chi 1 plus C2 chi 2. But I know that C1 equal to C2. So I can take C1 common. How do I find C1? You know. How do I find C1? I just
So normalization.
normalize this by 1. Now this one give you C1 square. Okay. Chi1 plus chi2 whole square d tau. And this one give you C1 square, chi1 square d tau plus C1 square, chi2 square d tau plus C1 square 2 chi1 chi2 d tau. What about chi1 square d tau? This is 1, no? Because each p orbital is normalized, no? Chi1 is a p orbital. This is also 1. What about this? This integral. This is S12, no?
0.
2 times S12. But this is 0 because Huckel approximation is 0. So what I have here is and that is equal to 1, no? Because it's normalized. So it gives you,
All
let us
over.
take this. Let us take this. If it is this case, so then phi 1 is your, sorry. Fine? This is phi 1. What about phi 2? How do I get phi 2?
X equal to 1.
Yeah. Now in order to find phi 2, put x, sorry, not x1, x is equal to 1. And if I put this is 1, 1, 1, 1. And you know that if I do this, what I'm going to get, because you have C1 plus C2 equal to 0. So C1 is minus C2. And if you do the same procedure, what I'm going to get phi 2. And you can guess what is phi 2. Phi 2 is 1 by root 2 chi 1 minus phi 2. Isn't it? Fine. So these are like two MOs. Can you draw these two MOs?
So bonding and anti-bonding.
Yes. So can you draw this? How does the phi 1 look like? So this is your phi 1 would look something like, because phi 1 you see, let me write down the expression here. Phi 1 is some constant, chi 1 plus chi 2, no? And chi 1, chi 2 are the pure orbitals. So essentially, the phi 1 would look something like this. This is your phi 1. And you have a nodal plane. What about phi 2? How does it look like, phi 2? This is C1, this is C2, no? How does it look like? See, you have minus sign here, no?
Two nodal surfaces.
Yeah, so you'll have something like this. So this is fine. So you're done with. Now what about the pi electron energy? Total pi electron energy. Some noise is coming. This is called E pi. Can you tell me what is this going to be?
2 beta.
No. See, what is the MO? What is the energy of the MO? Alpha plus beta, no? For each electron is alpha plus beta. How many electrons are there? It's 2.
2 into alpha plus beta.
This is your total pi electron energy. Now, this is a very crude theory. And alpha beta are not usually calculated from rigorous quantum chemistry. What is being done, that people do experiments, and from experiments, alpha beta are obtained. Alpha and beta. And then these values are put in this expression to calculate the pi electron energy. So this is, because of this is not a rigorous theory, very crude theory, and you have to get help from experiment. This type of theories, this is called a semi-empirical theory. This Huckel pi electron theory is called semi-empirical theory. Okay, and in most of the cases, alpha values are not needed. Can you tell me why? Because many cases people talk about the energy difference, and if you talk about the energy difference, your alpha will cancel, isn't it? As people are interested in, we are interested in
Electronic transition.
in energy difference rather than absolute energy between the MOs. Okay. One more information, and this is what I'm going to use. A typical value of beta is something like minus 230 kilojoule per mole. Okay, it is given from some experiment or from some rigorous quantum chemistry. You can calculate this, the typical value of beta, and this will be quite interesting. Okay, now next we move to the next system, 3 electrons, 3 carbon atom system. What is that system?
Sir,
Yes.
sir, when we are talking about pi electron energy, then then we will talk in the terms of resonance integral only. So if we see that 2 alpha plus 2 beta, it is going to be total.
Why resonance integral? I don't understand. This is the energy. Alpha plus beta. You have resonance as well as Coulomb integral.
Sorry,
Alpha plus beta. We just did the math, no? We did all the derivations.
yeah, okay.
Yes, it is alpha plus beta. You have both. Now, if you take the difference between these two, this alpha will cancel. Beta will only be useful. But if you want to consider, if you want to calculate the energy of the MOs or the total pi electron energy, then you have to know alpha and as well as beta. Okay, so now we move to the 3 carbon atom system. What is that system? Any idea what is that called?
Sir, allylic.
Yeah, this is like allyl system, no? It could be a radical, could be a cation, could be an anion, no? Could be anything, but so basically what I have here is C, C, C. Chi 1, Chi 2, Chi 3. Now tell me what, the Huckel matrix, how does it going to look like, Huckel matrix in this case? You know how to construct this Huckel matrix. Tell me. What are the diagonal elements? This will be 3 cross 3. Are you convinced because you have 3 carbon atoms?
Yes,
Yes,
sir.
sir.
Yeah, so what about the other terms? This is 1, this is 1. Again, this is 1, this is 1. This is 0, 0. Okay? Are you okay with it?
Yes, sir.
And then you have this. Okay? Now, if I, from here, if I go to the secular determinant and expand it, this one you can expand. How many of you can expand this?
Yes, sir.
This is x.
Yes.
I think you know this. X into x square minus 1 minus 1 minus 1, then x minus 0 plus 0. This is going to be x x cube minus x minus 2x. What are the solutions? What are the solutions?
So that is x into x square minus 2.
Yes. What are the solutions?
X equal to 0 and x equal to plus minus 2.
Plus minus root 2.
So let us do it. So you have one solution is other solutions are okay. This is not very difficult to do, isn't it? So let us do it. So I take this x is equal to root 2, x equal to 0. This one is actually what about this? This one 1, 2, 3. Okay, this is your bonding, no? This is called anti-bonding. And what about this? It's called non-bonding.
Non-bonding.
How many electrons are there in allyl system?
Sir, in cation 2, in radical 3, in anion 4.
Yeah, so I'll just put 2 here and consider cation. It doesn't matter. If it is cation, no? Okay. And actually, one can do, I'm not going to do it. You can do yourself. Now you know how to calculate the MOs. How do you do it? MOs? Tell me. It's phi 1, no? How do you calculate phi 1?
C1, C2, C3 for
Yeah, but how do you calculate C1, C2, C3? What do? You know the prescription. No?
diagonalize.
Yeah, you'll just take that value of x, put it in the matrix, and then find the relation between C1, C2, C3, and then you normalize the function, blah, blah, blah. And while doing that, you can calculate the coefficients, isn't it? So I'm just going to write down the expression. I'm not going to calculate it here. It is half phi 1 plus root 2 phi 2 plus phi 3. So this is okay. Now, can you draw these MOs? How do you draw this MO? The first one, say chi 1. You have 3 carbon atoms. Any suggestion? See, all are plus here. Can you see?
Yes, all are same sign at a side.
But the chi 2 has a factor of root 2. Half is common in all the cases. The root 2 is greater than 1, no?
Sir, for C2, coefficient will be greater than C1
so
and
for
C3.
this chi 2, the coefficient is slightly higher. So if you construct the MO, it is going to be something like this. This is your phi 1. Okay? What about phi 2? Phi 2, tell me. You should be able to tell me. See, phi 2 does not so actually, sorry, this is chi 1 minus chi 3. This is typo. Huh? Now, phi 2 doesn't have chi 2. So no zero coefficient of chi 2 is 0. Essentially, you have this. But you have a minus sign here.
Sign will be opposite, right? Means
This is phi 2. What about phi 3? I'll draw it here. Huh? It should be here, but since I don't have space, I'll draw it here. Phi 3, look at it. It is very similar to phi 1. Only the chi 2 has a negative sign, isn't it? More contribution, but negative sign. Okay? So this will give you something like this. There are plus, minus, this is plus, minus, but this is bigger, but negative sign. Okay? You're fine with it? Is it okay with all of you?
Yes, sir.
Okay.
yes, sir.
Now we'll come back to butadiene. Now butadiene we had started with, no? And butadiene had how many carbon atoms?
4.
And four carbon atoms. So you had 4 cross 4 matrix. If you go back, you see that the determinant was like this. X 1 0 0. Actually, you can write X X X X. Okay, then this is 1. This is 1. This is 1. This is 1, this is 1. Others are 0. And if you expand this, I'm not going to do it. You get x to the power 4 minus 3x square plus 1, 0. And it will give you 4 solution to your x. And these are minus 1.618, minus 0.618, plus 0.618, and plus 1.618. These are the values of x. Okay, and this will also give, now then it will give you the values of energy levels, epsilon 1, script 1, script E1, script E2, like this, script E3, script E4. So let us write it down. So let us go to the next slide. Write it down. So Anish, this was discussed, this pi electron MO Huckel theory, in any other course in chemistry, in organic chemistry or somewhere?
In organic chemistry, we study only the final expressions and the structure of the orbitals.
Okay, okay. So it is in 105.
Yes.
Okay. So let us do it here. So if I write down the energy, so let us draw the energies first. Okay. If we draw the energies, this is 1, this is equal to alpha plus 1.618 beta. This one is, you can guess this, no? This is 0.618 beta, no? Has to be. What will be the next one? Can you guess?
Alpha minus 0.618.
Yeah. This is 1 point, actually, I did it. Okay, these are the energy levels, and there will be corresponding phi's. I'm not going to calculate, I'm going to write it down. Phi 2 is and phi 3 is and phi 4 is okay. So these are the orbitals. Now, how many pi electrons are there in ethene? How many pi electrons are there in ethene? How many pi electrons are there?
Say butadiene, 4 pi,
So not ethene, butadiene. How many are there?
4 pi electron.
4 pi electrons. Huh? So they are going to be here, and so if I calculate, better to use this. If I calculate this E pi, what is this going to be? 2 into, just look at it, 2 into alpha plus 1.618 beta plus these two are in phi 2, no? Epsilon script E2. This will be 2 into alpha plus, sorry, 0.618 beta. What is this answer? It's 4 alpha, and you can just do this calculation.
4.472. Okay.
This is your energy. But look at carefully, what is this? This is butadiene, I told you, no? Now, if I consider only this part is something like similar to this part, no? So this is something like ethene. No, this is also ethene kind of thing. You have two ethene units. Obviously, they are connected to form butadiene. Had it been two ethene units, what will be the pi electron energy for that?
4 alpha plus 4 beta.
Yeah, it would have been, because for each ethene you have, you know, that 2 alpha plus 2 beta, no? Into 2. So this is different. So 2 ethene is not equal to 1 butadiene. Okay, fine with it. So basically there is an extra stabilization, and this is called delocalization energy. And that is equal to how much? This one minus this one, which is minus, not 4, 0.472 beta. So, and if I put the value of beta is minus 230. So this is roughly equal to 110 kilojoule per mole. So this amount of energy is the local is gain stability due to delocalization of pi electrons. And this is, I think, frequently used by organic chemists, isn't it? They talk about that, okay, this thing is stable because of delocalization of electrons. So the delocalization of electrons lowers the energy of the system. This is the typical organic chemistry way of explaining things. You knew about it, all of you?
Yes, sir.
Yeah. So let us now try to construct the MOs. That will be quite interesting. So for example, if I give you some expression, so you can construct the MO tentatively. If I give you an expression of phi 1 or phi 3, whatever, for some molecule, you should be able to construct the MO, no? I hope so.
Yes, sir.
Phi 1, tell me how it is going to look like. 0.37, 0.6, 0.6. So chi 2, chi 3 has higher contribution than chi 1. So this is not phi 1, this is chi 1, no? They should have told me, no? So chi 1 and chi 4, they have equal contribution, and chi 2 and chi 3, they have equal contribution, but they have different contributions. So can anyone tell me what is it going to look like? Let me draw it. So this one will be like this. This one will be bigger. This one bigger but equal. This one will be again same as. This is not a very good drawing, but it's fine. Fine, no? And this is a node you have. Nodal plane. What about phi 2? Can anyone tell me how does it look like, phi 2? Phi 2 is very similar to phi 1 in terms of coefficient, but signs are different, no?
Yes, sir. Ethane type.
And also their distributions are different. So if you see the 5, both are negative. Both are negative. One is 60, one is 37. Here both are positive. One is 37, next one is 60. So if I draw like this, it will be something like this. First one is bigger, like this. This will be minus, this will be plus. And here, it's fine? Fine with all of you? Not a very difficult thing to do. Are you convinced, all of you?
Yes, sir.
Not a very difficult thing to do. Because both are of same sign. That's why they form a bigger lobe. Minus. Here both are same size but positive, plus. You have a nodal. So you have two nodes here. On this, on this. 2. What about the next one, 5, 3? Let us try to draw this. If I draw 5, 3, how does it going to look like? See, look at it. 60, 37, 37, 60. And look at the sign. 60 means, okay, big. This should be equal anyway. Plus. What about the next one again? What about the next one? Again 60. Here also they are plus, minus, minus, so you can make a small lobe like this also. It's fine? How many nodes are there? You can go and check how many nodes.
There should be 3 nodes.
Where are the nodes, tell me?
So C1, C2,
Hmm.
and between C3 and C4.
These are the thing, no? Okay. What about let us draw this guy also. 5, 4. 0.37, 60, 60. Sorry, 0.37, 0.6, 0.6, 0.37. But you know the signal, the sign. 0.37 with minus, then 60 with plus, then 60 with minus, then 0.37 with plus. I don't expect you to remember all the expressions. Nobody can. But if I give you an expression, you should be able to draw the MO. Now, these are CC. Huh? How many nodes are there?
4.
There
Tell
should be
me.
4 nodes, right?
I can see one, this guy, this guy, this guy, this guy. 4, 3 nodes.
Sir, in the 5-3, I think C2 and C3, they should be merged, right?
You can make it like this if you want. Yes. That I told you, no? Yeah.
Yes.
So this is fine. MOs are fine. So I can move to the next molecule. And the last molecule I'm going to discuss in this course. Can you guess me? Can you guess what is that molecule going to be? Organic
Benzene.
chemistry. Yeah, benzene. Without benzene, you cannot have a course on organic chemistry, no? So let us do benzene. And let us draw benzene first and do it. So let us draw the ring and name them like 1, 2, 3, 4, 5, 6. So what is the size of the matrix? Huckel matrix in case of benzene.
6 cross 6.
So let us draw that write that matrix. What is the first term? X.
Yes.
So let us write the row first. X. Next one is what? 1, 2. They are nearest neighbor, no? 1. Then is 1, 3. 1, 3 is 0.
0.
1, 4 is
0.
1, 5.
0.
What about 1, 6?
1.
See, again 1, 6, because it's a cyclic system. Because of that, it is no longer 0, like in case of butadiene or anything. So they are non-zero, and this is 1, isn't it? That is how it is different, because 1, 6 are neighbors, like 1, 2. What about this? What about this? Actually, now you know that all the diagonal elements are going to be x. This is fine. And if I go to like 2, 1, like this is, first one is 2, 1. This is 1. What about this? This one is 1, 0. Okay. 0, 0. Are you guys there, by the way? 0.
Yes, sir.
Yes, sir.
1,
Yes.
1. This will be, tell me.
1.
1.
Why 1? Tell me. Why? What is this term? 3,
This is
3,
3,
4,
4.
and 3, 2. 3, 2, 3, 4.
3, 4.
What about this one?
Is 0, 0, 1, x 1, 0,
This one is
0, 0, 0.
0.
Yes.
Is it okay? 0. Then
1, 1.
this is 1, no?
Yes.
This is now again. This is
This is
1.
1.
yeah 1.
0,
0, 0, 0.
Or
1.
this guy.
Yes. 1x.
Okay, and you have 6 coefficient. So I do this. Now what should I do now? I should put this determinant equal to 0. I'll get a polynomial in x. What is the degree of polynomial in this case?
It will be 6.
Yeah, so let me write down. If I do this, I'll get don't worry, don't need to remember all these things, this all the details. And if I try to find the solutions, it is going to be x minus 2 . So what are the solutions? X is minus 2, x is 1. There are 2 times x is minus 1 and x, no, because these are square. These are 6 solutions. These are 6 solutions, okay? And if I draw the energy levels, let me draw it here. The lowest one is alpha plus 2 beta. Okay, so lowest one is alpha plus 2 beta. This is for x equal to minus 2, I guess, because you know x is alpha minus beta. And if I put minus 2, this means what? Minus 2, huh? Alpha plus. Okay, I'm just showing you only one term here. So the lowest one is alpha plus 2 beta. Remember, alpha and beta both are negative. Next one will be degenerate. Can you tell me what is this going to be? Can anyone tell me what is this going to be?
Alpha plus beta.
Actually, it's going to be alpha plus beta. But they are degenerate. Why degenerate? Because if I choose minus 1, I have to choose this twice. It's appearing twice. Next one is also degenerate. What is that?
Alpha minus beta.
And the last one is?
Alpha minus 2 beta.
How many electrons are there in benzene? 5 electrons.
6 pi electrons.
How we are going to put it? 1, 2, 3, 4, 5, 6. Isn't it? 3, 4, 5, 6. Okay. Okay. Now calculate this energy E pi pi energy. Tell me what is the value? 2 into alpha plus 2 beta, because 2 electrons are in this. 2, 3, whatever you want to call it. And next, 4 electrons are in alpha plus beta, no? Is it okay
Yes,
if I
sir.
write like this? So what is the answer? 6 alpha plus 8 beta. This is a pi electron energy for benzene. Okay with all of you? Is it okay?
Yes, sir.
Yes, sir. Yes, sir.
Now, again, draw benzene. If I view it as a combination of 3 ethene units, what will be the E pi energy? It will be
3 into 2 alpha
3
plus
into
2
2
alpha
alpha
plus
plus
2
2 beta. 6 alpha plus 6 beta. It basically means delocalization energy is how much? Tell me. It is 2 beta minus 2 beta
Right. Yes, 2 beta.
minus 2 beta, which is equal to 2 beta actually, which is equal to 460 kilojoule per mole. So which is quite huge. So that's why benzene is very stable and aromatic, no? Because aromatic molecules are also very stable because of this high delocalization energy. Of course, you count pi electrons, 2n plus 2, whatever, 2n plus 2, whatever is the rule is. But it also shows that your delocalization energy is quite large for benzene. Okay. So now next thing, what should I do? I should calculate the MOs of benzene. So it is quite involved. I'm just going to write down the expressions, what I did for butadiene. So let us write it down. Phi 1 is you should be able to draw this phi 1. It is not very difficult, no? All the orbitals have same contribution.
Right.
Okay. And the same sign. I hope I'm not making any mistake. I took it from somewhere. And you can calculate, for example, from the expression itself, the nodes. These are pi MOs of benzene. So maybe you guys had seen these MOs in organic chemistry course. How many of you have seen these pi orbitals? This pi mOs of benzene. How many of you?
Yes, sir.
So I'll show you a picture. So these are the picture. This is taken from the internet. Okay, this is pi 1 is your phi 1. Okay, all plus, all minus. We have one node. Node is the surface, is a plane of the molecule itself. This is pi 2, pi 3. They are of same energy, no? And then pi 5 and pi 4. They are of same energy, and then pi 6. I'm not drawing this, but you should be able to tentatively draw the MOs if I give you the expression, isn't it? With the sign. Here, red is plus, blue is minus. Okay? We'll stop here. And people had some questions on Coulomb integral. Somebody had a question. Is she here? I don't remember whom, but somebody had a question.
Sir,
So,
I already.
how many of you could evaluate the Coulomb integral? So, first of all, let me tell you, in the exam, I'm not going to ask a question like evaluate Coulomb integral, but it is good to at least give a try to calculate the Coulomb integral. Give it a try. You should try. Anish, did you try Coulomb integral?
Yeah, I could solve it, but I had to refer to a few
No,
textbooks giving some
that is
guide.
okay. That is okay. That is okay. So how did you do, Anish?
Uh,
Coulomb
so,
integral.
so the way I did it was that the R12 term has to be connected to R1 and R2. So using trigonometry and using the theta as the angle between R1 and R2,
Okay.
R12 can be connected to R1 and R2.
Okay.
R1, R2, and theta. Now, if you assume that R1 is along the z-axis, then theta becomes the azimuthal angle. So, we can then place it into the equation where the sine theta d theta term and this theta term will integrate, and then evaluate the R1 and R2.
So did you get the exact expression, the one I used in the class? I used
Yes.
something, no? It
Yes.
should exactly match.
5z by 8, I think.
Yeah. So problem is you're fine with S orbital. You can do it this way. In general, for H2 plus, it is done in not in spherical polar coordinate, but it is done in elliptical coordinate. Okay. All these Coulomb integrals and this other integrals you have. Okay. So this is how it is done. Did anyone try else? Try?
Yes, sir.
Yes, sir.
How did you do?
Sir, in the same way as
Same
explained.
way.
Yeah.
Sir, if we take that R1 greater than R2, then R1 to equal to 1 by R1 to equal to 1 by R1, and if R1 less than R2, then 1 by R1 to equal to R2. By this
Yeah.
approximation, can we do it?
Yeah. That is I think even easier way of doing this. Okay. So everybody knows. I don't need to demonstrate that. So anybody has had problem with Coulomb integral? Shonaldeep, did you calculate the Coulomb integral?
Yes, sir. I was trying to, but I did not finish.
Did not finish.
When I started
What about Dibbendu? Is he there? Dibbendu, did you do the calculation Coulomb integral? Did you do that?
Yes, sir.
How did you do?
In the same way, sir.
Same way. So good. So I think the best way to do is actually to assume that okay, when is R1 is greater than R2, you have this. When R2 is greater than R1, you have this. No, isn't it? Then the 1 by R12 will be replaced either by R1 or either by R2, depending on which one is bigger. Isn't it? Yeah, 1 by R12, no?
Yes, sir.
It is, you have, what is that expression? You have the expression that phi square 1 by r12 times phi square. Phi square 1s 1 by r12 phi square 1s, isn't it? That is what is Coulomb integral is.
Yes.
When r1 is greater than r2, your 1 by r12 will be replaced by r1, isn't it? And other way it will be replaced by r2. This is how it is done. Okay. Anyway, it doesn't matter in which way you have done, but you should do it once to get a feel for this. That what is this Coulomb integral? Okay.
So in exam we have to derive such kind of thing.
I don't think you will have to derive Coulomb integral. You can bring your whatever your calculator. So the exam will be in the assignment mode. Exactly what Rahul did. Exactly what Rahul did. In the assignment, I'll upload a question paper for CH425 as well as for CH812. Download it and then write it on a whatever page, white page with a blue or ink, black ink. Scan it, put your roll number, scan it, make a single PDF and upload it like an assignment. But you have to do it within 3 hours. So the exam starts at 8:30, it will end at 11:30. I think 8:30 is the time, no? Saturday, not this one, the next Saturday. Anish?
I think so, yes.
I think for both the courses. So this is how it is going to be. So did you enjoy this course, by the way? I don't know, because I can see only 20 people, 21 today. Last day it was like 29. It's like
Sir, I have
one is
one
orbital.
question.
Yeah.
Yes, sir. Sir, regarding the Coulomb integral, sir, I did one way, but using the elliptical coordinates, and then I think the integration would be very much easier.
Yeah, I told you, no. If you know the elliptical coordinate and how the variables, what are the limits of this variable, then you can do it.
So do I need to derive how the volume element in the elliptical coordinates, or you can simply use it?
You can simply use it, but I don't think you will get a question like this. I'm not going to give any question which will involve elliptical coordinate because I did not teach. But it is good to know, no? It is good to know.
Yes, sir.
Not that, see, if you take a course, you want to learn the subject, to have a good understanding of the subject. Second thing would be to score, get good grades, but nowadays the other way. And I'll stop presenting and stop recording.
Sir, could you please go to